Okay, this is section 8.5 for the online trig class, sum and difference formulas. In previous sections, we've had a lot of angles that we found and memorized, or if we didn't memorize them, we could draw triangles in certain locations to figure out their ratios. But what if you had a specific angle that you don't have a nice ratio for that you can memorize using the unit circle, say cosine of 15 degrees? Sometimes you'll be able to rewrite that as either the subtraction or addition of two angles that you already know. For example, cosine of 15 degrees, well, we know 45 degrees, and we also know 30 degrees for cosine, so if we have subtraction between those two, we would hopefully be able to do something with that. But how does it help us? So instead of going through the test, because you could just play around with this and see if you could come up with the answer, let's look at this from an analytical approach. So if you had just any two angles, say beta and alpha, beta being the smaller one and alpha being the larger one, we could talk about how that there are 2 points on that unit circle that coordinate with those angles. And remember, that's really how we find our ratios. So if we wanted to find the length between the 2 points, so we're trying to figure out what's the distance here, we could look at this using the distance formula, which the distance formula, if you haven't done that in a while, is d equals, and it's square root of x2 minus x1 squared plus y2 minus y1 squared, where these are just the pieces of the ordered pair. So for this would be cosine alpha, because I'm going to use P2 as my x2 and y2. So cosine of alpha minus cosine of beta squared plus sine of alpha minus sine of beta, because remember on the unit circle, cosine and sine of that angle relate to the actual x and y coordinates. So we're going to FOIL all of this out and see what we get. So this would be cosine squared alpha. You'd get minus cosine alpha, cosine beta, another minus cosine alpha, cosine beta. The way I'm figuring this out is I'm actually doing this by writing it twice and foiling in case you haven't done much multiplication with polynomials in a while. So this would be negative 2 cosine alpha cosine beta, and then negative cosine beta times negative cosine beta is plus cosine squared beta. And we're going to get a similar result with the sines, so I didn't square that, but let me put that in there. So this would be sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. Now, notice that I have a cosine squared alpha and a sine squared alpha. That is a Pythagorean identity, so we get a 1 for that. We also have a cosine squared beta and a sine squared beta. They're both positive. That's another identity, so we also get a 1. And then we have these two pieces, so this ends up being 2, because of the 1 and the 1, minus 2 cosine alpha cosine beta, minus 2 sine alpha sine beta. Now you think, okay, that's sort of interesting. It's just the distance formula. But what if we could face this triangle right here into standard position? So that would actually make, we've rotated it alpha by negative beta, essentially two angles being subtracted from each other. So if you put it in this position, you get now cosine of alpha minus beta, sine of alpha minus beta, and then this is standard position, so this is 1 and 0, because we're on the x-axis here. So this should be equivalent to what we just did here, except we've positioned this now in standard position. So this would be cosine of alpha minus beta minus 1 squared plus sine of alpha minus beta minus 0 squared. Okay, so for this one we have to FOIL it out again, so that would be cosine squared of alpha minus beta. This would be minus 1 cosine alpha beta minus another 1 cosine alpha beta, so minus 2 cosine of alpha minus beta. And then negative 1 times negative 1 would be positive 1, and this is just going to be the sine of that, so it's going to be sine squared of alpha minus beta. Again, we get the Pythagorean identity because of the cosine squared and the sine squared, so that makes another 1. So I have the 1 plus the 1, which is a 2, minus 2 cosine of alpha minus beta. Okay, so we're not quite done with this because we are using this to create the identity. So now we've set these two things equal to each other. This is the one we got when we were in standard position. This was just if the angle comparison was anywhere on the circle. If you square both sides, which is legal in an equation, you just have to realize that not all solutions may work. So sometimes when we're solving these, we'll have to check to make sure the solution works. This would give me 2 minus 2 cosine of alpha minus beta, because the square root would cancel out, equal to 2 minus 2 cosine of alpha cosine of beta minus 2 sine of alpha sine of beta. If we subtract the 2 over to solve this, that's going to cancel on both sides. So now we have this. And notice everything has a factor of negative 2. So if we divide that out, we'll actually get a formula for how do you subtract two angles and take the cosine of that. So cosine of alpha minus beta is cosine alpha cosine beta, because we've divided all the negative 2's out essentially, plus sine alpha sine beta. So even though I didn't write this in, I was dividing both sides completely by negative 2, which is why this went positive. So that's our formula for what if we wanted to do cosine of 45 degrees minus 30 degrees. This is how we would set it up. Now, we could also talk about doing the addition of two angles if we think about addition being subtracting the opposite. So that means that this would equal, using our formula we just derived, cosine of alpha cosine of negative beta plus sine of alpha and sine of negative beta. Because cosine is an even function, a negative inside is the same thing as having a positive inside. So that would be cosine alpha cosine beta. No negative anymore because those are equivalent. Sine, though, is an odd function, which means it has the origin symmetry. So that actually pulls a negative 1 out front of the sign when you have a negative inside. So that will change the sign of this second term, and then it'll turn back into just being beta. So notice that this formula is similar. You still have the cosine alpha, cosine beta, sine alpha, sine beta, but if it's a plus inside, we have a minus between them. If it's a minus inside, we have a plus. Now I have a way of remembering how cosine functions. Cosine functions, when you do sum or differences, they are antisocial and disagreeable. This is for cosine. What that means is cosines stick together, they don't mingle with anyone else, and the sines stick together, they don't mingle. That's what we mean by antisocial. Disagreeable means the sign inside is opposite to the sign in the middle. So that will kind of help you memorize that formula. So now we can go back and actually find what is cosine of 15 degrees without using a calculator. So cosine of 15 degrees, we would say is cosine of 45 degrees minus 30 degrees. Minus cosine, let's see. So there we go. Now we would write this out using our formula. So cosine of 45 degrees, cosine of 30 degrees. Since this is a minus, we would change to a plus, and then we would have our sines. So sine of 45 degrees, sine of 30 degrees. Cosine of 45 degrees is square root of 2 over 2. Cosine of 30, remember anytime you forget, you can always draw your little triangle. Here's 30 degrees, always across from 30 is 1. This is 30, 60, 90, so this is square root of 3 down here. So cosine is adjacent over hypotenuse, so that's square root of 3 over 2. And sine of 45 is the same thing as cosine. Remember, that's the 45-degree angle has the same two ratios. And then sine of 30 is opposite over hypotenuse, so that'd be 1/2. So this is square root of 6 over 4, because we can multiply the two radicals together. And then it would be plus square root of 2 over 4. So notice that we get the final answer, if we want to write it as one fraction, is square root of 6 plus square root of 2 over 4. Now, I would not approximate this unless it says 2 in the directions, which this doesn't. It says find the exact value, which means no decimals. So let's look at another one. So this time we want to do sum and difference formulas can be used in reverse. For example, cosine of 40 degrees, cosine 80 degrees minus sine 40, sine 80 degrees, where it looks like alpha is 40 degrees and beta is 80 degrees. So we first of all need to figure out which formula this originated from. So the cosines are together and the sines are together, but there's a minus between them. So that actually means that we were adding on the inside. Remember, it's opposite. It's disagreeable with this. So that means that this would be 40 degrees plus 80 degrees, which we don't know the cosine of either one of those groups. But if you add them together, you get cosine of 120 degrees. Remember, 120 is over here and has a reference angle of 60 degrees to the x-axis, which means this is square root of 3, a 1, and a 2 again, but this is a -1, so that's -1/2. Okay. Example 3 says let's find an exact value of cosine pi over 2 minus theta. So we're going to plug it into the formula. That would be cosine of pi over 2, cosine of theta. Since it's a minus and this is cosine formula, we become disagreeable. And then sine of pi over 2, sine of theta. Cosine of pi over 2, remember pi over 2 is right here up at the top. That's the 0.01. So cosine is actually of that is 0. So 0 times cosine theta is going to go away. And this would be 1 times sine theta. So this is actually just sine theta, which that makes sense because if you remember the graphs of sine and cosine, they are offset by a factor of pi over 2 of the wave. Okay, so then what we could do here, so this next piece says the results of example 3 will help us find an identity for sine of pi over 2 minus theta. So if we let that equal alpha, let's choose a different name for pi over 2 minus theta. That'll be alpha. Then this whole thing would be sine of alpha. Now cosine of pi over 2 minus alpha was from the identity we just did. And we showed that that was equal to, remember, sine theta. So cosine of pi over 2 minus theta, because that's, remember, alpha, on the right side, theta was replaced with pi over 2 minus theta. So that's what I just did. So this would be cosine of theta. And the reason that works is because the pi over 2's are going to cancel out. If you need to see that in great detail, you distribute that negative. And then notice those cancel each other out. So this is just showing you that this works either way. If you have cosine of pi over 2 minus theta, then it's going to be sine of theta. If you have sine of pi over 2 minus theta, it's going to be cosine theta. Now, whether or not you use that one a lot, that identity just depends on what you're doing. A lot of things you don't have to use every single identity. There are workarounds. But sum and difference formulas are things we do have to use. So let's consider the results that we just got to help us develop the identity for what happens if we want to add or subtract values inside of sine. So if we let alpha plus beta be theta, then we know that, remember, sine theta equals cosine of pi over 2 minus theta. So then if we replace that with alpha plus beta, again, turn it back into what it is, that would be cosine of pi over 2 minus parentheses alpha plus beta, so that's just turning back into that. And then we could regroup this, so notice right here, by regrouping and putting the minus alpha with the pi over 2, we're going to be able to use the factors that we just learned a second ago. So, okay, so here's what we have now. This would be cosine of pi over 2 minus alpha times cosine of now beta, because we're doing the formula, remember, for subtracting with cosine, which is cosine of your first angle, I'm just going to call it first, cosine of your second angle, and then plus sine of your first and sine of your second. So we're just trying to use this piece right here as our first angle, and this piece right here is our second. So you can kind of follow along. So cosine of that, cosine of this, plus sine of this, and sine of beta. So what ends up happening is that this guy turns, remember, into sine of alpha. Because when you see this pi over 2 minus alpha, that in a cosine, it goes back to being sine alpha. This would be cosine beta, this would be cosine alpha, and this would be sine beta. So what we've learned is that sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. So we've actually just proven from some identities that we've learned that that is now our formula. And then before we get too far, we're going to go ahead and show you the subtraction formula. So this would be sine of alpha cosine of negative beta, cosine of alpha sine of negative beta. When cosine is got a negative inside, it's even, so remember it just goes back to being beta. Sine, though, remember it changes sign, so that actually makes this guy -1 times sine of beta. And so what that does is that changes the sign in the middle. So this is sine of alpha minus beta. What you'll notice is that the sum and difference of sine, the sine part in the middle is going to match. But what's different is that the sines and cosines are intermingling with each other. So there's a summary chart here that shows you the two formulas for adding or subtracting angles inside of a sine. And the way I remember this is that these sine ones are social and agreeable. Because they intermingle. Sines and cosines mix together, but agreeable means that they match their original sign. So let's look at example 4. For example 4, we want to find the exact value of sine of 19 pi over 12. Now, you're going to have to find some way probably to add up to this or subtract down to it. A good hint is to try to think of just breaking this up into things that might reduce. For example, 16 is smaller than 19, and 16 and 12 have something in common. This doesn't always give you the right answer right away, but you can play with this. And the other thing that adds up to make 19 would be a 3, and 3 is also reducible with 12. So that would be, if we reduce that, that's 4 pi over 3 and pi over 4, which both of those we know the sine values of and the cosine values of. So this should work. So this will be sine of 4 pi over 3 plus pi over 4 equals, and our formula says we intermingle our sines and cosines, so sine of 4 pi over 3 times cosine of pi over 4. We're agreeable about our sine, and then we start with cosine the next time because you're going to use the alpha again. So 4 pi over 3 and sine of pi over 4. Now, again, you can refer to your unit circle, but sine of 4 pi over 3 is negative square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Cosine of 4 pi over 3 is -1/2, because remember 4 pi over 3 is in quadrant 3, so both parts are negative. And then sine of pi over 4 is also square root of 2 over 2. So if we work this out, this is negative square root of 6 over 4 and plus negative square root of 2 over 4. So I could write that as negative square root of 6 minus square root of 2 all over 4. Now, if you actually know one piece of or two pieces sometimes, about a sine of two different angles or a sine and a cosine of two different angles, you can still do these formulas. So notice in this scenario I have two different angles that they're referencing. Sine of alpha, so alpha is going to be one of my angles, is 3/5, but alpha has to be in quadrant 2. So I'm going to draw a picture just for alpha. And the reason it's in quadrant 2 is because pi over 2 to pi. So this one is for that. And alpha right here, so this is alpha, is got a sine of 3/5. So that would be opposite over hypotenuse. And then this is a right triangle, so we do need to find our other piece. So this would be 5 squared equals 3 squared plus x squared. That's 25 equals 9 plus x squared. That would be 16 equals x squared, so x is going to be 4, but we're in quadrant 2, so here x's are negatives and y's are positives. So the cosine of alpha, which is this angle right here, sorry I misdrew it a minute ago, is -4/5. Okay, so now let's talk about cosine of beta. How are we going to find that? Well, they've given us some information about beta. They said that beta is in actually quadrant 4, because it's between 3 pi over 2 and 2 pi. So I'm going to draw a triangle over here. So here's my beta, and it has -1 over square root of 5. So remember, sine is opposite over hypotenuse, and hypotenuse is always positive, so that's why I know the negative goes with that. And then I need to do Pythagorean Theorem again. So c squared is square root of 5 squared equals -1 squared plus x squared. So this would be 5 equals 1 plus x squared. So that's 4 equals x squared, or 2. And this time the x is positive because in quadrant 4 x's are positives and y are negatives. So this would be 2 over the square root of 5 if we write it like that. If we rationalize, remember the square root of 5 moves to the top and you get square root of 25 in the bottom, which is just 5. I usually go with the rationalized version when plugging into the other formulas. So now we want to do cosine of a sum and sine of a sum. So we need our two formulas. Remember, cosine is antisocial and disagreeable, so that would be cosine alpha, cosine beta stick together, minus, since it was a plus, sine alpha, sine beta. For the sine of a sum, we have that it is social and agreeable. So sine alpha is friends with cosine beta, plus cosine alpha is friends with sine beta. You just have to make sure each sine and cosine possibility has shown up. Okay, so let's plug in what we know now, because now we have all of our pieces. So cosine of alpha is -4/5. Cosine of beta is 2 square root of 5/5, minus sine of alpha, remember, was given to us originally in the problem as 3/5, I believe, but I want to look back up. Yes, 3/5. And sine of beta was negative square root of 5/5 when it was rationalized. So this is -8 square root of 5/25. Negative times negative would be positive 3 square root of 5/25. If these were not like radicals, we would just make this one big fraction, but because they're like radicals, we can actually add the coefficients. So this is -5 square root of 5/25, and the outside 5 is reduced, so it's negative square root of 5/5. Okay, so that's C part. For D, we have sine of alpha, which is 3/5, cosine of beta, which is 2 square root of 5/5, plus cosine of alpha, which is -4/5, and sine beta, which is negative square root of 5/5. This would be 6 square root of 5/25, plus, because it's going to be negative times negative again, 4 square root of 5/25. Again, we have like radicals, so that's 10 square root of 5/25, which reduces to 2 square root of 5/5. So therefore we now know the cosine and sine of the sum of alpha plus beta. Now then we get into how in the world would we deal with tangent, having a sum or a difference. And what happens here is that essentially, I'm not going to show you the whole how they figure out the formula, but I'm going to show you how they start it. Remember, tangent is sine over cosine. So essentially what they do is they write what those two formulas would look like. So this would be sine alpha cosine beta plus cosine alpha sine beta over cosine alpha cosine beta minus sine alpha sine beta. So if you start with that, and then and this is something you can do as long as you do it to both top and bottom of the fraction, what they do to fix this is they divide every single fraction by, or piece of this fraction, by 1 over cosine alpha cosine beta. Now since they're doing, now we're assuming then that those don't equal 0, cosine alpha and cosine beta, which any place that they would also cause problems for tangent. So what we're doing here is we're just multiplying this through, and that will give us this, you'll get these tangents on top, you'll get a 1 right here because that's exactly what we divided by, and then you'll get the tangents back to back on the bottom. So the formula is it's tan alpha plus tan beta over 1 minus tan alpha tan beta, or if you're doing subtraction, there's a minus and then a plus. So the only thing that changes between the two formulas is where the plus and the minus shows up. So the top always matches and the bottom is different. So now if we wanted to find the exact value of tan of 2 pi minus theta, if we use our formula, that would be tan of 2 pi minus tan of theta, since it matches that on top, over 1 plus tan of 2 pi tan of theta. So tan of 2 pi, remember 2 pi is right here, that's the ordered pair 1, 0. Remember, tangent is y over x. So this is for 2 pi. This would be 0 over 1, which is just 0. So that means this is 0 minus tan theta, so that'd be negative tan theta on top over 1 plus 0 times tan theta, which is going to cancel out. So you just get negative tan theta over 1, which is negative tan theta. Okay, so our last page in this section, we're going to try to use some combinations here to solve something a little bit more complex, some substitution ideas. So we want to know the exact value of cosine with a bracket, sine inverse of 2/3 plus tan inverse of negative 3/4. So if we let alpha be sine inverse of 2/3 and beta be tan inverse of negative 3/4, we could rewrite both of those, remember, in terms of the tangent and sine of theta or alpha. So this is just using the inverse definition. So this would be sine alpha equals 2/3. Remember, sine is only defined when you're using inverses back and forth, when alpha is going to be between negative pi over 2 to pi over 2. So we do have to worry about our restricted domains. The other situation is tan of beta equals negative 3/4 when beta is, remember, between negative pi over 2 to pi over 2, but not including those because that would cause undefined. So then what we can do with this is we can actually talk through, remember, our sine rules for our trig functions. So essentially we're stuck in these two possible quadrants. That's it. That's our only possibilities. So either quad 1 or quad 4. Sine is only positive up here because remember, all science teachers are crazy. That says that sine is positive in 1 and 2. So since we only have 1 at our disposal, we're going to use this one. So let's put our information here. So this is going to be alpha, and this would be opposite over hypotenuse, and we're going to use Pythagorean Theorem to find that x. So that would be square root of 5, and it's positive since we're in quad 1. Tangent of beta, we need tangent to be negative. Well, tangent's positive in quad 1, so it has, and its cosines are positive in, because everything, remember, is positive in quad 1. Cosines are the only positive ones down here, so it has to be down in this quadrant. And we don't know that these triangles are the same size, so I'm sort of drawing them off scale a little bit. This is, and in fact, I should have probably drawn it a little longer than the other one because it's a 3 for the opposite, but it doesn't matter. Again, drawing to scale doesn't always matter as long as you can find your pieces. So I didn't mean to erase my picture. All right, so tangent, remember, is opposite over adjacent. So that's 3 and 4. And we have to make sure the negative goes on the correct one, which would be the y value. So this is, we're solving for the actual r squared this time, or c squared if you want to think of it that way. So that's 16 plus 9, which is 25, so that's 5. Okay, so now that we have those pieces, we need, if we want to use the, okay, so look what we're ultimately trying to do. We're trying to do cosine, and this cosine has an addition sign between it. So essentially we're trying to do cosine of alpha plus beta, because alpha and beta, remember, are standing in for those big things that we were given inside. So this means that we need to be doing cosine alpha, cosine beta, minus sine alpha, sine beta. So the thing is, we need all of this information from our picture. That's why we had to draw the picture. We already knew sine of alpha, so I'm going to go ahead and list that one over here. That one was 2/3. That was right here when we did this conversion. Tangent beta didn't help us with any of these pieces. It just helped us figure out the triangle. So let's go ahead and get cosine of alpha. Alpha's up here, so that'd be square root of 5 over 3. We want to do sine of beta. So beta's down here, so that's opposite over hypotenuse, so that would be negative 3 over 5. And cosine of beta, which is adjacent over hypotenuse, so it should be positive 4 over 5. So now we have all of our pieces, we can plug them in and get the actual answer to this really complex thing by using substitution is what we did. So cosine of alpha is square root of 5 over 3. Cosine of beta is 4/5. Minus sine of alpha is 2/3. Sine of beta is negative 3/5. This is 4 on the square root of 5 over 15. Negative and negative make a positive 6 over the square root of, over 15. And we don't really have a way to add those together since one of them is a radical and one of them is not. So we write it as one big fraction. And I got ahead of myself writing. So 4 square root of 5 plus 6 over 15. Okay, and our final one, this is solving a trigonometric equation, linear in sine and cosine. So we have both a sine and cosine at the same time, and usually when you're trying to solve an equation, you only want one of those. So one of the tricks is to try to square both sides. You do have to keep your restrictions in mind, but this would be sine theta minus cosine theta times sine theta minus cosine theta. Now again, this is not the only way you can do this one, but this is an effective way. Over here, the negative gets squared so it becomes positive, and square root of 2 is just 2. If we FOIL this out, this is sine squared theta minus sine theta cosine theta minus another sine theta cosine theta plus cosine squared theta, because it's negative times negative. So we get this Pythagorean identity that's hidden in here. Sine squared theta plus cosine squared theta is a 1. And then I get minus 2 sine theta cosine theta, since they're like terms. I would subtract the 1 over. So that makes that 1. You could also divide by -1, I guess, if you wanted to. I'm going to leave this like this for a second because we still have a problem of having what I call a sine and a cosine both in the same equation. Now, I want to talk about what this actually equals. This is actually jumping ahead to the next section, but if you remember, we have sine formulas for adding two things together. So this is theta plus theta, because let me just show you what happens if you do the same angle added to itself with the formula. So this would be sine of theta, cosine of theta, plus, because it's agreeable, sine of theta, cosine of theta. This actually equals 2 sine theta, cosine theta. Another way of writing this is sine of 2 theta, because it's 2 thetas that I added together. So this whole thing right here is actually equal to sine of 2 theta. I wish they'd held off on putting this problem in this section because they really were trying to lead you into solving this with a much harder way, and it's much easier if you know what we call the double angle formula. We will formally define this in the next section in 8.6. So if you have this, some people like to think of this as what we call a U substitution. Now this is something that is covered in like Math 136, where essentially you let this be just sine of some random angle U. And then we ask, when would sine of an angle equal -1? Now there's only one scenario where sine, which is the y value, equals -1 on the unit circle, and that's down here. So this would say that U has to be 3 pi over 2. Okay? Now that's also assuming that we haven't went around the circle multiple times. If we do go around the circle multiple times, we would add a factor of what we call 2 pi k, where k stands for integers. In other words, anytime we map back to this specific point in time, that means that we are going to get this value. So if you add 2 pi, you're going to end up in that same location. Now why this is important here and why we have to do it here is because we actually weren't solving for u. We were solving for 2 theta. So when you get to this point, you have to set 2 theta equal to your answer, which contains all your coterminal angles as well. So then what we do to solve this for theta, which was our true variable we wanted to solve for, is we divide everything by 2. So that makes this 3 pi over 4 plus pi k. Now what we have to consider at this point is, what if k was, I always do a few options. If k was -1, 0, 1, or 2. So if k was 0, that's the easiest one because that would just go away and you'd have 3 pi over 4. If k is -1, you would have 3 pi over 4 minus pi, which you can write as 4 pi over 4. So that would be negative pi over 4. If it was 1, we'd have 3 pi over 4 plus pi, which would be 4 pi over 4 if we made it into a common denominator, and that is 7 pi over 4. And 3 pi over 4 plus 2 pi, which if we wanted that to have a common denominator, it would be 8 pi over 4, and that's 11 pi over 4. Now we could keep doing that forever, but we don't really want to because this was only defined between 0 and 2 pi. So that means some of those possible solutions are already without fail going to be wrong because they do not fall in our little restricted answer zone that we gave ourselves. So negative pi over 4 is not between 0 and 2 pi because it's counting the other direction. And 11 pi over 4 is bigger than 8 pi over 4, which is 2 pi. So it has to either be 3 pi over 4 or 7 pi over 4. It could be both, but you'd never know until you actually plug them in and check. So our original problem was sine of theta minus cosine of theta equals negative square root of 2. So I'm just going to check this really quick using my calculator to show you that one of these actually works and the other one doesn't. So it's really important to sometimes use your calculator and check. So I'm going to have to put myself in radians. So sine of, oops, sorry, I need to enter my angle first. So 3 pi, it didn't like the 3. So 3 times pi divided by 4, and then I'm going to take the sine of that. It's just going to keep it going for me, and then I have 7 times pi divided by 4, and then that is a cosine, and then we want to hit enter and see what that equals. Okay, now notice it kept all of my stuff inside that. It worked it out for me. Notice that that's negative 8.79. So when I got this one plugged in, I got negative 8.79. We're going to check that against the negative square root of 2 in a minute, but I'm pretty sure that's not right because square root of 2 should not be 8. And then we're going to do 7 pi over 4. So 7 times pi divided by 4, and we're going to do sine of that, minus 7 times pi divided by 4, and that's going to be cosine, and then we're going to hit enter, and notice this time I get negative 1.41. Now, if you take the square root of 2, notice that it is the 1.41 case. So that means this does not plug in correctly. So the only solution between 0 and 2 pi for this specific theta is 7 pi over 4. So just because you get a solution doesn't mean it always plugs back into an equation correctly, especially if you're dealing with a restricted domain. Because there's lots of angles that would have given us that location, but the restricted domain cut down our group of possibilities, and then we also found out that one of them didn't work. So that is the end of section 8.5.